Hey everyone, welcome back to another video in our course Introduction to Linear Algebra. We will be continuing our discussion on elimination that we started in the last couple of videos, where we're going to introduce matrices as actions. Here we have this system ax equals b. It's a linear system of equations, three equations in three unknowns, x1, x2, and x3. What we did last week was we set up this system, we set up the augmented matrix as follows. 2, 4, negative 2, 4, 9, negative 3, negative 2, negative 3, 7. And then we augmented the vector b, 2, 8, 10. And then what we did was we wanted to carry out elimination. So we took that first pivot, this was the first pivot, and we used it to eliminate underneath the pivot. That operation associated to elimination under the first pivot, well, there are actually two operations. So the first operation that is responsible for reducing this 4 was R2, the second row, minus 2 times the first row, and this was written as a new row. Now for the third row, the operation was R3 plus R1 into R1, and this produced an equivalent system, so not the same, but a system for which the same x's would work that looks like this. 2, 4, negative 2, so nothing changed in the first row. And then in the second row, we got a 0 in this position under the pivot as we wanted. Then we have 9 minus 8, that's a 1. Negative 3 plus a 4 is another 1. 8 minus 4 is 4. Now in the last row we're adding, so 2 minus 2 is a 0, 4 minus 3 is a 1, negative 2 plus 7 is 5, 2 plus 10 is 12. So we got this simplified system. Now what happens in the simplified system? Recall that the first column here is coefficients for x1. The second column is coefficients for x2, and the third column is coefficients for x3. Well, looking into the first column over here, you see that only the first row has x1, has a non-zero coefficient for x1, whereas the second and third rows, they have these zeros, which tell us that x1 does not show up in the second and third row. So we've carried out an operation on the rows of the original matrix A. We arrived at some different matrix, call it B, for example, or C or D, doesn't really matter. But what matters is that we applied elementary row operations. So these operations on the rows are called elementary row operations. And what we will see today is that these operations can actually be represented as matrix multiplication. So elementary row operations which are these things over here, can be represented as matrix multiplication. And these matrices are called elementary matrices. So using elementary matrices. Our task in this video is to figure out how to find these elementary matrices and how they represent these operations and why we would want to represent these operations as in the form of matrices. Now, continuing our discussion, we first have to start with a very important matrix called the identity matrix. So the first matrix we want to consider is the identity matrix. What does identity stand for? So usually in math, identity stands for doesn't do anything. So we need a matrix such that when we apply it, it doesn't do anything. And what do we mean by apply a matrix or a matrix action? So by matrix action, we really mean matrix multiplication. In other words, when we multiply by this identity matrix, we want it to do nothing, and to do nothing on, let's say, on a vector. So given a vector x with, let's say, 3 components, x1, x2, x3, the identity matrix denoted I satisfies I times x equals x. Now, I will tell you what this matrix is. So for a vector with 3 components, this identity matrix is always a square matrix, so always 3 by 3 or 2 by 2 or 4 by 4. In this case, I has a very special form. In the first column, it has 1, 0, 0. In the second column, 0, 1, 0. In the third column, 0, 0, 1. Let's see that this matrix really satisfies this equation over here, that Ix equals x. Let's multiply. So I times x is the matrix 1, 0, 0, 0, 1, 0, 0, 0, 1, times the vector x with components x1, x2, x3. Now remember, we can carry out multiplication of a matrix by a vector in 2 ways for the time being. The one would be rows times vectors, so using dot products. The other one would be treating the product as a linear combination of the columns as follows: x1 times 1, 0, 0 plus x2 times 0, 1, 0 plus x3 times 0, 0, 1. Now, notice that in the first column here, the non-zero term is in the first position, so this x1 is going to go there when we multiply the 2. For the second vector, x2 is going to multiply this 1, so it's going to go in the second position, and x3 is going to multiply the third component, go there, because the other components are just 0, so nothing will happen. So you see that this really is equal to x1, x2, x3. So this matrix, the identity matrix, doesn't do anything. This is absolutely crucial. And when we say doesn't do anything, we mean doesn't do anything under the operation of multiplication. Now, let's talk about elementary matrices. So the identity matrix is a type of elementary matrix, which will be absolutely crucial for us. But we want to actually find matrices that represent elementary row operations. So let's talk about an example here. What matrix represents, let's see, these operations, let's say one of the operations, this one, R2 minus 2R1 into R2. So we want a matrix that represents R2 minus 2R1 into R2. How do we find this matrix? So the system in question, this is very important, the system that we have has 3 rows. So then the matrix that we want, this elementary matrix that needs to represent this operation, has to be of size 3 by 3. So 3 equations dictates elementary matrix of size 3 by 3. So that means 3 rows and 3 columns. What's the procedure? Apply the operation R2 minus 2R1 into R2. So apply this operation onto the identity matrix. And the resulting matrix will represent the operation R2 minus 2R1 into R2. So let's do this. This is the procedure, if you wish. We start with the identity matrix 1, 0, 0, 0, 1, 0, 0, 0, 1. We apply this operation R2 minus 2R1 into R2, and we obtain this new matrix. So the first row stays the same, 1, 0, 0. The second row says R2 minus 2R1, so we have a 0 minus 2 times 1, that's a negative 2. Then we have 1 minus 2 times 0, so that's just 1. 0 minus 2 times 0, that's 0. Nothing has changed in the third row, so we just copy it down. So the matrix we were looking for is this one. Let's name it E. Now let's check that when we apply this matrix on a vector, it's the same as if we applied this equation. So let's take this matrix, 1, negative 2, 0, 0, 1, 0, 0, 0, 1, and apply it on a general vector, x1, x2, x3. What will we get? We could carry out the multiplication rows times the vector, so using dot products, or we can use we can use linear combinations. Just for the sake of saving space, let's carry it out first row times column, second row, third row, and so on. So when I apply the dot product of the first row times the vector x, I just get 1 times x1 plus 0 plus 0. So this is just x1 over here. Now when I apply the second row dot product with this x, I get negative 2 times x1 plus x2, and then plus 0 times x3, so I'm just not going to write that. And then I have the third row times x. The first two components are 0, so x1 and x2 don't show up, and then I have 1 times x3, so that's x3. Now, let me do the following. Let me take the vector x1, x2, x3, and apply the operation R2 minus 2R1 into R2. What do I get? Well, I'm not saying anything should change in the first or third component, so I know that I have x1 in the first component and x3 in the last component, and then I just have to apply the operation to the second row. So I have x2 minus 2x1 into the second row, and you see that the two vectors are the same. So whether I apply this operation on the vector x or I multiply the vector x by a matrix, I get the same result. But look at the difference. Here I have equality. Here I have an arrow where I'm saying I'm changing the original vector into a different vector. Well, now with these matrices, we have a precise way using an equality to say how the vector changes. And that will be very important when we want to find a way to reverse these operations. So what if I want to go back or retract my steps? This is where the elementary row operations will come in handy. Another type of elementary row operation is exchanging two rows. So I perhaps should say here, rather than an example, that will be the first type of operation. So when we try to carry out elimination, we could do an operation of this kind where we are trying to eliminate. So normally if you had such an operation, what you're trying to do is you're trying to eliminate in that space with this pivot. So you could have this type of operation. Another operation could be that we want to exchange two rows. So how do we exchange two rows? And really, the same idea would apply if we wanted to change arbitrarily many rows. But the strategy is the same. Apply the operation to the identity matrix. And you will have gotten your matrix. Now, so in math, exchanges are called permutations. We'll call this type of matrix a permutation matrix. And let's say we decided to change row 1 with row 2. The idea of how to get this permutation matrix is the same as before, just apply it. So apply the row exchanges to the identity matrix. So the exchange of row 1 and row 2 applied on the identity matrix gives us 0, 1, well, I should write probably with the rows, 0, 1, 0, 1, 0, 0, 0, 0, 1. And this matrix will be called a permutation matrix P. Let's see that the action of P is exactly what we claim it to be. So if we apply the matrix, so let's look at P times X on some vector X. We have 0, 1, 0, 1, 0, 0, 0, 0, 1 times some vector x1, x2, x3. Now note that 0 times x1 is just 0. Then 1 times x2 is x2, and 0 times x3 is x3. So when you multiply the first row by x, you just get x2. So the first component is x2. Then for the second component, 1 times x1, that's x1. 0 times x2 is 0. 0 times x3 is 0. So we just get x1. And then finally, the third row times x gives us x3, which is the same as applying the operation r1 exchange r2 onto this vector. We would get exactly that vector. Let me write that just for completeness. So if we were to take the vector x1, x2, x3 and apply the operation of row exchange r1, r2, we would get x2, x1, x3, because that's exactly what the operation is telling us to do. One last type of elementary row operation, which we haven't used so far, but we will use soon enough. This would be to multiply a row by some number. So multiply a row by a constant. For example, constant C. We'll call this matrix again an elementary matrix denoted by E. It's close enough to what we want, it doesn't change the rows. But let's look at an example of what this could be. So let's say we have this matrix with components 2, 2, 4, and then 1, 2, 3, and then 1, 7, 4, for example. And we want to carry out elimination. But this first pivot is a 2, and we see that 2 is a common multiple everywhere in the first row. So let's say I wanted to create a 1 there. I would want the first row to be like this. So I would want the matrix to be 1, 1, 2, 1, 2, 3, 1, 7, 4. So you see the second and the third rows are just copied. But I would want to change that system into this system with 1, 1, 2. Although I don't really have an augmented matrix here, I could put some B vector. But the idea is we can do this. So how do we do it? Well, the operation in question would be to multiply the first row by 1/2. So if you multiply by 1/2, it's the same as if you divided by 2, and write that as the new row. This would correspond to something like this. If you had 2x1 plus 2x2 plus 4x3, you would want, let's say that's maybe equal to 0, for example, and you would change that to be x1 plus x2 plus 2x3 equal to 0. These are equivalent systems, and this is something that we commonly do in math because, well, it's just nicer to work with this equation because the coefficients are smaller or whole numbers and things like that. So sometimes if we have a fraction, we may want to multiply by a whole number to get rid of fractions. So how to get this operation, or what matrix represents this operation? Well, it's done in the exact same way. Just apply the operation to the identity matrix. To get the corresponding elementary matrix. So if we start with the identity. Ones along the diagonal, zeros everywhere else. We apply this operation 1/2 R1 into R1. And what that means is that I just have to multiply every number in the first row by 1/2. So I will get 1/2 in the first position, 0, 0. And then the second and the third rows remain the same. So this would be a scaling operation, if you wish, or a scaling matrix, but we still refer to it as an elementary matrix. All right, with this, we'll close in this video.